The netstat, network statistics, command is used to display information about network connections, routing tables, and various network interface statistics. When listing active sockets, the state column shows the current condition of a TCP connection, which follows a defined life cycle from initiation to termination. Here is a summary of the most common TCP states you will see in netstat output, organized by the connection phase. 1. Connection establishment phase. These states are part of the three-way handshake. State role description. The socket is ready and waiting for an incoming connection request. Listen server, a client SYN segment. This is the state of a typical server process. The client has sent a SYN, synchronize, segment and is waiting for SYN_sent client the server's response, SYN ACK. This indicates an active open. The server has received the client's SYN, sent a SYN ACK, and is SYN_recv server now waiting for the client's final ACK. The three-way handshake is complete. The connection is open, and established. Both data can be transferred in both directions, full duplex. 2. Connection termination phase, four-way teardown. These states reflect the independent closing of the sending side by each endpoint. State role description. The local application has initiated an active close, sent a FIN active FIN_wait_1 segment, and is waiting for an acknowledgement, ACK, from the closer remote side. Active. The local side received the ACK for its FIN. It is now waiting only FIN_wait_2 closer for the remote side's FIN segment to complete the close process. The local side has received a FIN from the remote end and passive acknowledged it with an ACK, passive close. The local close_wait closer application must now close its socket to proceed. A high number of sockets in this state often indicates an application bug. The local side, which was the passive closer, has now sent its passive last_ACK own FIN and is waiting for the final ACK from the remote side closer before moving to closed. A rare state that occurs when both sides simultaneously send a closing both FIN, simultaneous close, and are waiting for the final ACK from the other side. The local side has completed the four-way handshake. It waits for active 2x maximum segment lifetime, MSL, to ensure any delayed time_wait closer packets are cleared from the network and the remote side received the final ACK. 3. Final state role description. There is no connection state at all. The connection entry is removed from the closed both connection table, and therefore, from netstat output. Understanding these states is critical for network troubleshooting, as seeing too many connections in states like SYN_recv, close_wait, or time_wait can indicate specific performance or application issues. TCP reliability mechanisms. The Transmission Control Protocol, TCP, is renowned as a reliable transport layer protocol. It achieves this reliability by implementing a series of complex mechanisms designed to detect and recover from packet loss, corruption, duplication, and out-of-order delivery, which are common occurrences on the underlying, unreliable Internet Protocol, IP, network. Here is an introduction to the primary TCP reliability mechanisms. 1. Sequencing and ordering. To ensure the data stream is reassembled correctly, TCP assigns a unique identifier to every byte of data sent. Sequence numbers. Each segment sent carries a sequence number in its header, which indicates the byte number of the first byte of data in that segment. This allows the receiver to identify if any data is missing and correctly reorder segments that arrive out of sequence. Ordered delivery. The receiving TCP layer holds segments that arrive out of order until all missing segments are received. Once the data stream is complete and in the correct order, it is passed up to the receiving application. 2. Acknowledgement and retransmission, error recovery. TCP employs a system called positive acknowledgement with retransmission, PAR, to guarantee delivery. Cumulative acknowledgements, ACKs. The receiver sends an acknowledgement number in the TCP header, which specifies the sequence number of the next byte it expects to receive. This implicitly acknowledges all previous bytes. Retransmission timeout, RTO. The sender maintains a timer for every segment it transmits. If the sender does not receive an ACK for a segment before the RTO expires, it assumes the segment, or the ACK, was lost and retransmits the data. The RTO is dynamically adjusted based on the measured round-trip time, RTT, of the connection. Fast retransmit. To avoid waiting for the full RTO, the receiver sends a duplicate ACK whenever it receives a segment out of sequence. If the sender receives 3 duplicate ACKs for the same data, it immediately assumes the missing segment is lost and retransmits it without waiting for the timer to expire, significantly speeding up recovery. 3. Error detection. TCP ensures the integrity of the data being transferred. Checksum. The TCP header includes a 16-bit checksum that is calculated over the header, the data, and a pseudo-header containing key information from the IP header. The receiver performs the same calculation. If the calculated checksum does not match the value in the header, the segment is considered corrupted, is discarded, and is not acknowledged, forcing the sender to retransmit it. 4. Connection management. Reliability begins with a formal agreement to communicate. Three-way handshake. TCP uses the SYN ACK process to establish a connection. This ensures both the sender and receiver are ready, active, and agree on the initial sequence numbers, which is the foundation of reliability. 4-way teardown, the connection is closed gracefully, fin, ACK, fin, ACK, ensuring that both sides confirm they have finished sending and receiving all data. These mechanisms work together to guarantee that the application receives an identical, error-free, and ordered stream of bytes, regardless of the intermediate network conditions. The retransmission and timeout flow in TCP is the core mechanism that provides the protocol's reliability. It ensures that every single byte of data reaches its destination, even if segments are lost or corrupted in transit. There are two primary ways a TCP sender detects and recovers from a lost segment: 1. Retransmission timeout, RTO, the standard, time-based recovery. 2. Fast retransmit, the quicker, event-based recovery. 1. Retransmission timeout, RTO, flow. The RTO mechanism relies on a timer to detect segment loss. A RTO calculation, the timer, round-trip time, RTT, measurement, the sender measures the time it takes to send a segment and receive its corresponding acknowledgement, ACK. This is the measured RTT. Dynamic adjustment, since RTT fluctuates with network conditions, TCP uses a smoothed, or weighted average, of recent values, called the smoothed RTT, and a measure of the variation, RTVAR, round-trip time variation. RTO value, the calculated RTO is the duration the sender is willing to wait before declaring a segment lost. This value is calculated dynamically for each connection and is typically bounded, example usually never less than 1 second, with a maximum of 60 seconds. Karn's algorithm, a crucial rule, states that the RTT of a retransmitted segment should not be used in the calculation, as it is ambiguous whether the ACK received is for the original segment or the retransmitted one. B. Timeout flow 1. Transmit, the sender transmits a segment and starts the RTO timer for that segment. 2. ACK received, if an ACK for the segment arrives before the RTO expires, the sender stops the timer, uses the measured RTT to update the RTO calculation, and continues sending data. 3. Timeout occurs, if the ACK does not arrive before the RTO expires, the sender assumes the segment, or the ACK, is lost. 4. Retransmit and backoff, the sender immediately retransmits the lost segment. Critically, it then uses exponential backoff to set the new RTO. The RTO value is typically doubled with each successive retransmission attempt for that segment. 5. Congestion control penalty, a timeout is considered a strong signal of severe network congestion. TCP reacts by reducing its data transmission rate, typically by resetting the congestion window, to its initial, smallest value, often 1 MSS. 2. Fast retransmit flow. Fast retransmit is a heuristic designed to detect and recover from single segment losses much faster than waiting for the RTO to expire. A. Duplicate ACKs out of order receipt, when the receiver gets a segment that is out of order, meaning a segment earlier in the sequence is missing, it cannot acknowledge the out of order data. Duplicate ACK sent, the receiver sends an ACK segment with the acknowledgement number set to the sequence number of the missing byte. This ACK is a duplicate of the last ACK successfully sent. B. Fast retransmit trigger 1. Sender receives duplicate ACKs, the sender continues to send new data segments as long as its window allows. Each time an out of order segment arrives at the receiver sends another duplicate ACK. 2. The threshold, when the sender receives 3 duplicate ACKs for the same sequence number, it is a strong signal that the segment immediately following that sequence number has been lost, since 3 new segments have arrived following the missing one. 3. Fast retransmit, the sender immediately retransmits the missing segment without waiting for the RTO timer to expire. 4. Fast recovery, unlike the RTO, fast retransmit suggests that the congestion is minor. Instead of resetting the to 1, TCP switches to the fast recovery congestion control state. This allows the sender to maintain a higher transmission rate, avoiding the severe throughput drop caused by a full RTO. In essence, RTO is the ultimate guarantee of delivery but incurs a high performance cost, while fast retransmit is a rapid, graceful recovery that maintains better throughput in the face of minor, isolated losses.